Welcome to this lecture series in number theory. In this lecture, we'll look at a very interesting coin problem due to Frobenius and also see a general framework in which to fully address it. Or maybe not fully, but sufficiently address it. We need to know about GCDs and Bezout's theorem. We have seen these things many times, so I'm not going to recall these statements and definitions. You can go back to the previous lectures if you're unsure. Okay. So what is the coin problem? Or what is a version of the coin problem? The original coin problem was slightly trickier. So suppose you have a 3 rupee coin, or not just one, you have a lot of 3 rupee coins and a lot of 5 rupee coins. Let's say you have infinitely many of both of them. And just a note, today these things are not available. The 3 rupee coins no longer exist, but who cares? Mathematically, it's fine. So we have an infinite supply of 3 rupee coins and an infinite supply of 5 rupee coins. And suppose we want to pay someone some sum of money. And this is all that we can muster. This is all that we can use to pay that sum. Now, what one cannot do is pay the guy 1 rupee. Using only these denominations, one can't possibly pay someone a sum of 1 rupee, right? One cannot also pay a sum of 2 rupees. But one can pay a sum of 3 rupees because I could just take out a 3 rupee coin and give that to the guy. So this is possible. What about a 4 rupee coin? What about a sum of 4 rupees? No, I can't. This is not possible. 5 rupees, yes. A 5 rupee coin will do. So 5 can be paid. I think orange was a better color. 5 can be managed. What about 6? Yes, 6 can also be managed because 6 is 3 plus 3. 2 3 rupee coins will do. 7, well, if you think a little bit about 7, I don't think you can. Whatever you do, it will never be 7. What about 8? Yes, you can manage 8. Because 8 is 5 plus 3. Right? 9, clearly we can do 9. Because 9 is 3 times 3. What about 10? We can do 10. What about 11? We can also do 11 because 8 plus 3 is 11. So for 11, you can use 2 3 rupee coins and 1 5 rupee coin. 12. Yes, 12 can be managed because 12 is a multiple of 3. What about 13? 13 is also fine. Because 13 is 8 plus 5, so you can use 1 3 rupee coin and 2 5 rupee coins. So the point is, even though we weren't able to pay off some of these numbers initially, these were beyond our reach, but after a certain point, we are seeing that you can manage everything else. Right? So this phenomena is what I'll call the Frobenius coin phenomena, although what Frobenius asked, if you look at the Wikipedia article at least, what Frobenius asked is what is the smallest natural number which has a property that beyond that point you can always pay off a sum of money of that value. So after 8 you can do everything, and this is the Frobenius number associated with these two coins. Right? So the minimum beyond which you are happy, beyond which you are comfortable. But that's not what we will prove. That's not what we will discuss. What we will show is that there is some such number that beyond that number you can always pay off a given sum. So that is what we will prove. It's not obvious that such a number exists, right? There were certainly a few objections in the beginning. Why should the objections suddenly stop? So we will prove that the objections do suddenly stop. Okay. So we will talk about some number theoretic aspects or number theoretic things, and then we will come back to the coin problem. The connection is very, very clear though. So let's forget about the coin problem for the moment and let's consider this equation. And we want to find all the integer pairs x and y which solve this equation. Right? One can always ask for real numbers which solve this, but that's not very interesting. We are asking for integer solutions to this equation. In general, solving an equation in integers is very hard. But in this very simple linear situation, we understand the phenomena very well. And this is just a toy example, which we will build to get we will be building towards a general theorem, which we will see maybe in the next slide or so. So anyway, let's just focus on this particular little problem for the moment. Okay, so let's at least find one pair of solutions. By Bezout's theorem, we know that the solution does exist because the GCD of 2 and 3 is 1. By Bezout's theorem, we know that there do exist integer solutions to this equation. And it is easy to find one such pair of integers, namely if you take x as 2, or let me call it x naught. So here is the solution. So let x naught be equal to 2 and y naught be equal to minus 1. So then clearly 2x naught plus 3y naught equals 1. So this is just one solution. Are there other solutions? Well, certainly there are. For example, well, what others are there? Yeah, you can take x as 5 and y as minus 3. That will also do. There are many other solutions. Can we characterize them? So say we have some other pair of solutions, some other pair xy, which is a solution. Solution to star, where what is star? Star is this equation as star. So suppose 2x plus 3y is 1 is what I'm saying. So then we subtract these two things, these two equations we subtract. What do we get? Then twice of x naught minus x plus 3 times y naught minus y. This is 0. Okay? This is very clear just by subtraction. And now, what do we see? We get twice of x naught minus x is 3 times y minus y naught. Right? I just took this thing to the other side and shuffled the things here because there's a minus sign that will come up. Fine, so we have this. But what does this give us? It gives us that 2 divides the right hand side because it divides the left hand side. But the GCD of 2 and 3 is 1. So 2 has to divide this thing. This part should be very clear. This is all the dropping property. We discussed some properties of GCDs. We are using here the dropping property. So this implies 2 divides y minus y naught. And by the same reasoning, it also implies that 3 divides x naught minus x. But let's ignore this thing for the moment. We have 2 divides y minus y naught. So therefore, it is necessary that y is equal to y naught plus 2t for some integer t. Right? Great. So what does that give us if we substitute this expression for y here? So let me call it something. Let me call this dagger. And this I can call as maybe clubs or broccoli. So using broccoli in dagger, broccoli and dagger together give us that twice of x naught minus x is equal to thrice of 2t. Right? If you substitute y as that expression, then this becomes that thing. Great. So what does that tell us? This gives us that x naught minus x is 3t. And there is something not right here. No, it's fine. So we get x is equal to 3t, x naught minus 3t. And what we had darkened here is already happening. So we didn't really need to take note of this separately. This already implied that this must happen. Okay, so what do we see? The upshot from both these things, broccoli and let me call it broccoli prime. So from broccoli and broccoli prime, we can conclude that there exists an integer t such that this deserves a separate color. So there exists an integer t such that x equals x naught minus 3t and y equals y naught plus 2t. So this is necessary. Whenever we have a pair, a pair which solves this equation, an integer pair that solves that equation, it is necessary that there will be such an integer t such that these two equations hold. But the converse is trivial. If you take x as that and y as that, it is trivial to verify that this equation will be true. Why? Because twice of x naught minus 3t plus thrice of y naught plus 2t, this is equal to twice x naught plus thrice y naught minus 6t plus 6t, which is 2x naught plus 3y naught, which is 1 because x naught and y naught were chosen as such. So therefore we have a complete list of solutions. The complete set of solutions is this: x naught minus 3t, y naught plus 2t, t an integer. This is exactly the list of the set of all possible integer solutions to this equation. Okay, so we'll just turn this into a theorem now. Suppose a and b are relatively prime, and suppose there is some, we know by Bezout's theorem that there do exist integers x naught and y naught such that this equation is satisfied. Then we claim that this, all the pairs of this form where t is an integer is precisely the set of all the solutions of this equation. So this is exactly what we observed when a was 2 and b was 3 in the previous example. And we can repeat that reasoning to prove this in general. So here is the proof. Let x comma y be a solution. So this be such that ax plus by is 1. We already have that ax naught plus by naught equals 1. Subtract to get this equation, which gives ax minus x naught equals minus b, or I'll just write it as b times y naught minus y, which implies a divides y naught minus y. Why? Because a divides the right hand side, b is relatively prime to a, so you can drop it and conclude that a divides y naught minus y. And similarly, you also can say that b divides this, but we ignore that. So therefore, you write y as at minus y naught for some integer t. Or maybe I should write y naught minus at. That's correct. Yeah, this is correct. So we have that, and now if you plug this in, here, if you plug this equation here, what you get is x is x naught plus bt, right? Because this a will cancel off, and yeah, whatever we saw in the previous example. So then what we see is that if this is a solution, it has to lie in that set, because x is of this form, y is of that form. Any solution has to lie in that set. But it is trivial to verify that anything in this set is a solution to our equation given here. Okay, so nothing more interesting than what we already observed in the previous example. We just wrote it in general. So the whole trick is to find one solution. Once you find one solution, you are through. Then you can express all the other solutions in terms of that one solution. And to find that one solution is equivalent to, it's just Euclid's algorithm. So you can find that one solution very fast using Euclidean algorithm. We discussed how to find GCDs using Euclidean algorithm, and it's basically that. Note that this is also same as asking for how to find the inverse of A modulo B, right? That's exactly what this equation is all about. Anyway, but here we are trying to do a more qualitative analysis rather than some algorithmic thing, at least for this lecture. So let's move on. So this time we have some other equation, slightly different equation. We want to find all pairs of integers which solve this. So clearly solving the given equation, 4x plus 6y equals 8, is equivalent to solving 2x plus 3y equals 4, because we can cancel the 2 from both sides. We cancel the 2, we get this. So this is what we want to solve. Okay. All right. So the same story will go over here. Can we first find one solution? So to do this, one solution is very easy to find, because first you solve this equation. Let me write this down in a slightly de-highlighted way. First you solve this equation. Maybe I'll put a tilde over here. This we know how to solve, because this we know one solution. One solution is x naught is 2, x naught tilde is 2, and y naught tilde is -1. And then you just scale both of them. So then if you scale x naught tilde and y naught tilde by 4, you get x naught is 8 and y naught is -4. So clearly this is true. If you substitute x naught as 8, you get 16 over here, and y naught is -4, you get -12 over here. You add them, you get 4. So to find one solution to this, you first solve this equation, because GCD of 2 and 3 is 1. So by Bezout's, you can easily solve this equation by employing the Euclidean algorithm or by guesswork. Once you find solutions x naught tilde and y naught tilde, you just scale them by the number written over here, and you will have found at least one solution to the given equation. But we are trying to characterize all the solutions. So now I will continue with the usual. So say 2x naught plus 3y naught equals 4 for some integers x naught and y naught, and we saw that they do necessarily exist, because even if you had written a 1 over here, such x naught and y naught would exist, and you can just scale them to get a 4. So fine, and one particular solution has been written over here. All right, now say we have some other solution. And the same story, subtract to get, and blah 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 blah. You will write that x is x naught plus 3t, y is y naught minus 2t for some t, right? For some integer t. By the same reasoning, and therefore any pair of solutions, any x and y which satisfy this equation, have to have this form, that x is of this form and y is of that form for some integer t. But again, it is trivial to verify that any such thing, any such x and y, you choose an integer t, whatever you want, and assign x as this value and y as that value, it does satisfy this equation. So it's almost the same as when we had one written over here. Instead of a 1, we have some scaled 1. Okay, so we can now turn this into a theorem. Suppose a and b are integers, not both 0, and n is some integer, and consider this equation, ax plus by equals n. We want to ask if one can solve this, and if one can, what are all the solutions? Can we characterize the solutions? So, to answer the existence question, let's say D is the GCD of A and B. We claim that the equation has a solution if and only if D divides n. Note that it is necessary for D to divide n if there were to be a solution. If there are integers x and y satisfying this equation, then it is necessary that D divides n because D divides the left-hand side. D divides A and B, so it has to divide n. So if there is a solution to this equation, D must divide n, and we will look at the converse. Why is it that if D divides n, this equation has a solution? That's basically Bezout's theorem. Further, we can characterize all the solutions, and that's written over here. Once you find a solution, x naught comma y naught, all the other solutions are like this. So you can read, rather than me reading it out, you can just pause the video and read this. We have seen this in an example just previously, so I don't want to spend too much time here. Okay, great. So let me first argue this part. Why is it that if D divides n, then this necessarily has a solution? So this equation, suppose D divides n. We have already argued the other direction, so suppose D divides n. Then solving this equation is equivalent to solving this equation, a by d times x plus b by d times y equals n by d. Right? Because n is divisible by t, this is an integer, and these are anyway integers. So instead of working with that equation, we can work with this equation, and it helps because the GCD of a by d and b by d is 1. This is the scaling property, if you will. Right? So this equation does have a solution. Why? Because this equation, this has a solution by Bezout's theorem. A by d and b by d are relatively prime. They have GCD 1. So this has a solution. And therefore, once you find a solution to this equation, you just scale the solutions by n by d. That serves as a solution to this equation. So I'll just say that which does have a solution. And the reason is Bezout's theorem. Okay, great. So we have justified this part of the proposition. Now we want to say that all the other solutions look like this. One direction is clear. If you just take anything of this sort, that will necessarily satisfy this. No question. That is very simple, just algebra. So we will show that every other solution is of this form. And again, it's just that subtraction business. So say x naught and y naught are some particular solutions. Say this happens, and this also happens for some x and y. So then subtract. We get a by d times x minus x naught plus b by d times y minus y naught is 0, which is the same business. It gives us that a by d must divide y minus y naught. Right? A by d, it divides this guy, so it must divide that guy, but then it is relatively prime with the b by d, so it must divide this guy by the dropping property, and therefore you can write y as let me write this as y naught minus y. It doesn't change anything. It's just to be compatible with the blue thing. It is exactly the same statement as previous one. So we have that, and therefore y is equal to y0 minus a by d times t for some integer t. And as we saw, this forces that x is x0 plus b by dt. Right? If you substitute this, if you substitute this in place of y here, you get x is that. So if x and y solve this equation, they necessarily are lying in this set. The pair x comma y is lying in this set, and anything that lies in this set solves this. So it's very easy. It's very easy to characterize the solutions of this. First, you check if GCD divides the right-hand side. If it doesn't, no solutions can exist. If it does, find one solution by hook or by crook or by using Euclid's algorithm. Once you've found one solution, you can express every other solution by just forming this set. As simple as that. So it is a very simple, palatable answer to a difficult looking question. And now we can come back to the coin problem. So the coin problem in abstract mathematical terms, suppose we have relatively prime integers a and b, then there is some natural number n such that whenever you pick something at least that natural number, whenever you pick something at least that natural number, you can find non-negative integer solutions satisfying this equation. Okay? So, and this is the coin problem, because coins cannot be paid in negative. They can only be non-negative number of coins that you give to someone. Therefore, it is important to have this in order to solve the coin problem. I mean, this is basically modeling the coin problem is all I'm trying to say. Why is this true? Since a and b are relatively prime, we have some solution. Say ax0 plus by0 equals n for some x0 and y0. We know these exist by Bezout's theorem. So we know x0 plus b by dt, comma y0 minus a by dt are all the solutions. So we want to show that if n were large enough, if n were sufficiently large, there is an integer t, such that both coordinates of a solution are non-negative. Right? This is what we want to do. If n were large enough, then there is something here in this set whose both coordinates are positive. Right? That's what we want to do, which I have just restated. That if n were large enough, there is some t in this, t is some integer t, such that both coordinates are non-negative. So that's all that I am saying. Maybe I said positive when I was rehashing, but I meant non-negative. Okay. So how do we show that this happens? Well, first let's rewrite these equations in a single equation. That is t should be at least minus, there must be some integer t between minus dx0 upon b and at most dy0 upon, sorry, this should be a by d, right? This is a by d upon a. So what have I done? I've written this equation as that, and I've written this equation as that. So I've just written both these equations in this fashion. So what do we want to do now? We want to show that if n were large enough, there is some integer t such that this holds. Okay? And now here is the point. We want to show that if n were large enough, and note that these x0 and y0 are depending on n. N is nowhere to be seen here, but x0 and y0 are depending on n. So we want to show that if n were large enough, then there is some integer t sandwiched between these two real numbers. So, suppose we are given two real numbers and are asked if there is an integer between them. In general, it is a hard question. But suppose we know that the distance between those two those two real numbers is big. Let's say the distance is bigger than 1. Then clearly there has to be an integer between them. What I am saying is, suppose you know that you have been given two real numbers and they are far apart. If they are far apart, then there has to be an integer between them. And by far apart, I just mean greater than distance 1 apart, or at least distance 1 apart. Here we are not having strict inequalities, so we are fine with distance equal to 1 also. All I'm saying is that if these two numbers are far apart, at least distance 1 apart, then such an integer t will exist. So enough to show that if n is large enough, then this absolute value is at least 1, but just for simplicity, I'll write strictly greater than 1. I hope these steps are clear. This is where the difficulty arises in the Frobenius coin problem. This is where we are sort of weakening the thing. We are not able to find the smallest such n. We are just happy with one n which makes this true. For there to be an integer t between these two numbers, it is not necessary that these two numbers are distance 1 apart or more than 1 apart. It is just sufficient. And that is what we are exploiting. So it is enough to show that if n were large enough, this holds. But what is this? This is, if you do the algebra, this is nothing but d times by naught plus ax naught divided by ab, absolute value. But what is this number? This is n. Ax naught plus by naught was n because x naught and y naught were chosen as such. So dn upon ab. So we want to show that if n is large enough, this happens, which is true. A, b and d are fixed numbers. If you choose n large enough, clearly this inequality will hold at some point, and that's it. So I hope these steps were clear. This is an interesting piece of reasoning, not a very difficult one, but interesting. This is a non-trivial problem. Okay? So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.